All right, thank you everyone for sticking around for the last talk. So I'm Wuzhong Li. I'm going to talk about this package Echopype that we are developing right now to help us increase the interoperability and scalability for processing specifically ocean sonar data for obtaining biological information. Before I jump into the talk, I want to first acknowledge my collaborators. Valentina Steneva, she's a data scientist at the eScience Institute at UW, and also Kevin Nguyen. He is a senior undergrad student from the Department of Physics, and he just joined the development in the spring, so that's why you don't see his name on the abstract, but he had made a significant contribution to this. So I want to first start with some introduction of what is sonar, because I realize not every one of us deal with sound all the time, right? So sonar, here I'm going to talk about the active form of acoustic sensing. So sonar stands for sound navigation and ranging. So basically you send out signal, and then you analyze the returning echo to understand the environment, right? So on the left-hand side is a typical scenario when we use human-made sonar system to understand the interior of the ocean. On the right-hand side are echolocating animals. Oh, there's a typo, I'm sorry. Echolocating animals who use sonar either in the air or underwater to navigate and forage. And sonar is everywhere, actually, in ocean sciences. So here are a few examples. On the top here is the acoustic Doppler current profiler that is virtually on all the research vessels, right? And then on the bottom here is a side-scan sonar image. We use side-scan sonar to obtain, look at features on the seafloor. And there's also the echo sounder or fish finder that is kind of the workhorse for looking at marine ecosystem at the mid-trophic level. So if you want to analyze, or if you want to observe fish and zooplankton distribution in the ocean, a lot of people use echo sounder. And then on the bottom here is multi-beam sonar mapping, right? So if you want to map how deep the seafloor is, what's a feature like a seamount, then a lot of people use multi-beam. Today, I'm going to focus more on the echo sounder part to look at biological information. So that's what the talk focuses. So with all the acoustic instruments in the water, we have become very, very good at collecting data, right? Especially in the past 15 to 20 years, there has been a boom in deploying autonomous ocean observing systems. So here I'm showing you a few examples. So we have a lot of moorings, for example, from the US Ocean Observatories Initiative, the Canada, Ocean Networks Canada. There's a lot of mooring that's basically stationary echo sounders pointing up from the seafloor and just collecting data 24/7, streaming to shore, right? And then there's the NCEI from NOAA, which is the National Centers for Environmental Information. They have archived all the water column sonar data in the past 20 to 30 years. And then more recently, people are putting echo sounders or different type of sonar systems on all kinds of autonomous vehicles. So here, this is the wave glider. This is sail drone, and then there's also all kinds of underwater gliders that people use, right? So we are actually having a lot of data right now, and this data has the spatial and temporal coverage that's much greater than we had before, at least like 20 years before, or even 10 years before. And it provides excellent opportunities for us to understand the marine ecosystem, especially under this time with all the climate change problems. And I just wanted to show you a few examples of large-scale sonar data. So on the left-hand side here, I'm going to first, maybe this one, this is cursor better, probably. On the left-hand side is an example of large temporal scale data. So the example I'm showing is from the OOI endurance array. This is from a cabled echo sounder moored at 200-meter water depth and looking up. What you're going to see here is a set of rolling echograms. So echogram is basically a representation of sound amplitude as we receive from the sonar. So what you are seeing here on the three panels are basically the vertical axis is depth, horizontal axis is day. The brighter colors are higher reflections. So basically, this is where animals are in the water column. And we use 3 different frequencies because that's a way for us to tell what's in the water. It's either fish or zooplankton or something else. They have different frequency signatures. So we have a lot of data from the ocean observatories. This is a set of 12 months of data. but the data actually has been flowing for more than 4 years right now. And there are not just this one node, right? So there are 6 of them, and there are another 3 on the east coast, right? So this is an example of large temporal scale data set. On the right-hand side is a large spatial scale data set. Different from this upward-looking sonar system, what you are looking at here now is actually a bird's eye view looking down at the surface of the ocean. So in this case, the sonar is looking horizontally. And that's why you can see the scale here is X and Y in kilometers. So in this case, you are seeing 3 by 3 quarter of the ocean. In the middle, this bright spot is the echo from a shipwreck. And in the local ecosystem, this shipwreck becomes an artificial reef. And this is interesting because what we found out is that if you look at the echo signature at dusk, you started to see all the reef fish that was hiding in the artificial reef started to spread out at dusk. And this is pretty cool because you can look at this kilometer scale phenomenon. And actually, the entire data set is covering a 20 by 20 kilometers square of the ocean, so it becomes very interesting. So this is basically just two examples of large temporal and scale data set. And of course, there is more data with both large spatial and temporal scales, right? So these are from the NCEI data set. And these are just in the US. There are a lot from all these other countries in the world, right? So this new data brought a lot of opportunities, but also a lot of new challenges. Here I'm laying out the differences, So I use different colors of rectangles to denote data from different type of instruments. And each block is just a kind of a representation of a quantity. So it used to be that we have discrete data set from one instrument, and we just analyze that data for a specific hypothesis we want to look at, right? But right now, what we have is this. We have all this data coming in all the time, and they are from different instruments, and they are, there is a very large volume of data. So we really need to figure out what's going on, and to be more specific about the challenges of big acoustic data. And I realized this is a bad problem, so I just underscore them, is that there is an interoperability problem because we have many different types of sonar systems from many different manufacturers. They all have their manufacturer-specific binary format, right? And people use a lot of proprietary software or open source software written in proprietary languages to analyze this data. But they're all very, very specific for sonar systems. So once you wanted to start combining data, you start to run into all kinds of wrangling issues. And another set of problems are scalability issues, right? So the current analysis workflow is very labor intensive, and I'll give an example just in a minute. And there's currently no support for parallel computation with random access file format. So what I'm showing here is a typical fisheries sonar data analysis pipeline. We start from the left with downloading or accessing data from a server, and then very quickly import all this data into a software and to do pre-processing like calibration and denoising of the data averages. And then it goes to the expert scrutiny stage, which actually requires a human to sit there and scroll through the echogram to look at interesting features. And then we can go into advanced processing to do species classification or biomass estimation, so on and so forth. And then once we reach this stage, we can then finally analyze and then answer our scientific questions in ecology or fisheries, right? But then we all know what the problem is here. In the middle, there is a human sitting in the middle of the loop, right? It's really difficult to scale up, even though it's a very valuable stage of analysis. And then we need to toss the data back and forth between different software, which increase the overhead of doing any type of operation. And in addition to interoperability and scalability problem, there is also reproducibility problem that we need to deal with, because currently most of the analysis software is done by GUI. GUI is great because you can explore your data, you can visualize everything in a very meaningful way, but it's very difficult to reproduce. And then there's also a challenge in terms of community engagement, because if we are talking about changing all of the above, then we really need to change the workflow that the community as a whole is engaged with, right? And then, so we are talking about trying to do community-level, community-driven development, and hopefully coming up with data standard, which I'll actually spend some time talking about later. So I've talked a lot about the challenges. I want to talk a little bit about the vision, right? So I believe we can deal with all this problem that we talked about before, right? So our vision is we can develop analysis method and software tools to tackle the challenges, and then reach an end goal to be able to basically integrate data from heterogeneous instrument sources, and then perform synoptic analysis of the marine ecosystem over large temporal and spatial scales. Right. And our long-term goal is that we wanted to be able to make ocean sonar data a more general or a more integrated component of the oceanographic data set. And it is right now somewhat more of a spatialized data set, and there's no reason it has to be that way. So this is our long-term goal for this development. For this talk, I'm going to focus on the software tool part. So why do we need new software? We kind of already touched upon that, right? So this is the current workflow, which requires extensive data wrangling. So we have a lot of instruments that's collecting collecting data. And if we want to clean and combine all the data together, we need to toast the data between multiple software packages and trying to figure out. And then finally, you can perform your actual analysis. But doing data wrangling, as we all know, is very exhausting and expensive if you're dealing with proprietary software. What we really should be doing is to spend time here instead of on the left-hand side. But what's happening right now is it's so hard to do the data wrangling process. We spend most of our time and resources trying on the left-hand side of the figure, and that's not what we wanted to do, right? And we believe we can do better by leveraging the scientific Python ecosystem, because the wider geoscience community has already created a lot of tools to solve similar problems. So we decided that let's just build a package to handle the left-hand side of the figure. And this is where Echopype comes from, right? So what we wanted to do is to simplify the data, I think this, okay. To simplify the data wrangling side of things so that we can actually spend more time on the right-hand side. We want to be able to actually do the back and forth, not on the data wrangling part, but on looking at developing better existing analysis routines, or incorporating newer or machine learning type of data-driven analysis to help us answer scientific questions in marine ecology or fisheries, right? So this is kind of the reason why Echopype come into play. So the next, I just wanted to give you an overview of where we are right now in terms of developing and the development of Echopype. This is the workflow that I'm just going to use a cursor, if I can. Okay, so on the top left corner is where we started, right? Echopype basically operates by converting all the raw data into a netCDF file, or a standardized netCDF file format. The reason why we're doing that is because once we can get the data out from manufacturer-specific file format, there's a lot more tools that we can use. Currently, we follow the ICS Sonar netCDF 4 convention for raw data storage whenever possible, and I will talk a little bit more about this later. So as we talk about, once we get the data into a standardized format, we can then take advantage of existing libraries like Xarray and Dask that has been mentioned earlier. And also this provides the users a more uniform interface so that it's much easier to use. And then you can develop whatever computational pipeline you want after that point, right? So this is what we're doing right now. And once we get into this, we can then start to dream about what type of fancy visualization or more advanced analysis you want to do with sonar data. And as we all know, to be able to analyze the sonar data, you need to calibrate the system and also perform pre-processing, such as denoising and averaging. So those are actually included in Echopype as well, because we view it as an integrated part of the data analysis pipeline. So in terms of data representation, I just want to talk a little bit about why we chose to use netCDF. Because the raw sonar data are really just numerical arrays, right? It's just numbers representing the amplitude or phase of the sound signal they receive at the transducer. So we did consider NumPy, right? So NumPy arrays are simple to use, especially for MATLAB users. But it has to do all the operations in memory. it doesn't support label indexing for time, like the pinning time of the sonar, or the depth, or the sonar frequencies that actually include a lot of information for analysis. It also doesn't support metadata, right? And that's why we decided to go to netCDF, because with more complex structure, netCDF files allow direct access for more efficient data selection and subsetting. It has support for labeled data set for scientific interpretation. There are existing libraries for visualization and scalability. And there are also conversion tools. If we decided to move things into the cloud, we can easily do that by converting data out of netCDF file format. Right? So this is why we decided to go that route. And now we have seen roughly how Echopype looks like. I wanted to show you a notebook that demonstrates Echopype, basically. And the example I'm going to show is to look at a set of sonar data that was collected during the 2017 eclipse time. The data was collected by the upward-looking sonar echo sounder that's moored offshore Oregon that happened to be in the totality zone. So it was actually a pretty cool data set. What I'm going to show in the notebook, there are two things that we did. So basically, the first is on the top, we access the OOI data, process using Echopype, right? So that gets our sonar observation. And then the second part is to access the solar radiation data from the National Data Buoy Center, because that actually gives us the real, how much light are these animals actually receiving at that time, right? And then we combine those and then visualize. And the good thing, one thing that I think is important for this is if without Echopype, if you want to do this, you need to import data into different software and then finally export it and to be able to do it. But what I'm going to show you is you can actually do it in a few lines of code. I mean, many cells in the notebook, but you can do it in one notebook, right? So this is a binder, and I guess I'm not connected anymore. But we did deploy a binder that you can access from the Echopype GitHub repository. So you can all run this. So basically, in the beginning of the notebook, we show how you can process one file, because if you can process one file, you can process many files, right? So we first just install Echopype and then download data from the Ocean Observatory's Initiative Raw Data Archive, and then just process that. These are a few lines of code. It's essentially 5 lines of code that does the data wrangling for you, right? So it basically convert everything from raw file to netCDF file, and then perform calibration, remove noise, and then get an average tile type of sonar representation. Huh? The what? Font? Yes. Is that better? OK.
Even more.
All right. All right. So that's bigger. OK. So yeah. So basically, it's 5 lines of code that does the data wrangling for you. And once you do this, we can open the data set as Xarray data set, and then you can just plot without actually having to write anything to plot the echogram, right? And this doesn't make any sense, I know. It's just color figure, but it proves that it works, right? And then after this, we can then process many files and then put it all together. I'm going to skip the middle because it's just a lot of messages. But when we assemble all of them, this is what you get, right? So this is the echogram from the day of the eclipse. And again, this is an echogram. The vertical axis is depth. Horizontal axis is time, right? So these are the pin time. The time shown here are in UTC, so you need to -7 to get to the Pacific local time. But what you're seeing here is the very strong signal on the top are basically like surface reflections, right? So reflection from the water surface, because the sonar is looking upward. What you see here, this blip going up and down, these are actually the animals' response to the solar eclipse, because without this blip, what animals are doing is this regular DL vertical migration, right? So animals were higher in the water column during the night, and then once it comes down, it moves down, and then stay there for the whole day, and then goes back during the night, right? But something happened, so there is an abnormality here. So this is the Echopype processing part. We then get the solar radiation data from the National Data Buoy Center, and then plot it. So it looks like that. right? So this is kind of nice because it has a very strong signal. We know when a solar eclipse happens, right? And then now we can then put it together at the end of the notebook. And this is kind of cool because you can then see almost perfect mirror image on the top and the bottom, right? You know that when the solar radiation dips, the animals were kind of fooled by what's happening in the world and then trying to go back to the surface until it doesn't look like that anymore. So go back to the depth of the water. So this is a very simple demo of Echopype functionality, but I hope I had convinced you that this is easier than tossing data between different software. So, and then now you can move back to the slides. All right. So having shown how Echopype stands right now, I want to talk a little bit about the challenges that we saw on the way and the way going forward. Right. So one main thing that we didn't think was such a big deal, but actually is a very big deal right now, is we need to have community input for the Sonar data format. We try to follow the ICS Sonar netCDF 4 convention as much as possible. And this was actually pretty new. Like, this was published last year. But then we decided to actually store multi-frequency data as n-dimensional arrays instead of separate data sets or data arrays in the file, because it will actually facilitate processing, especially if you want to use Xarray. So that's a major deviation from the current convention. And also, the convention only deals with storage of raw data, but Echopype also supports preprocessing. So what about the process data? Like, how do you store that, right? So there needs to be more from the community. I actually didn't show it. OK, so there needs to be more from the community to decide what to do as a whole, like how to go about solving all this problem. And there are some problems here or issues here, right? Because we can try to be as generalized as possible, or we can try to be more efficient, right? What is the right balance to do, to decide? And are we just trying to create another standard when there are already many standards, right? So there has to be a community-based conversation to move forward. So that's one of the main issues. The other part are more on, we just wanted to grow Echopype better. We wanted to support more Sonar data formats. Right now, we can support conversion and processing for 2 types of Sonar models. We wanted to add the broadband echo sounders. If any of you deal with acoustic data, it's a big thing in the past 5 years. We want to also be able to deal with all the ADCP data conversion, because people have been using ADCP data for current measurement for the longest time. But there has always been this kind of, on the back of a mind, can we just use this to measure biology, right? And it is possible to do, especially a lot of ADCP manufacturers are actually changing the way they digitize the data. So, so we want to include ADCP, and hopefully we can support this soon. And we also wanted to streamline deployment of Echopype on the cloud. And there are all these hurdles that all of you have been talking about, right? And very importantly, we want to engage the community in testing and developing this together. And this is an important cultural change aspect that has to come into play for this to be successful. So this is the GitHub repository for Echopype. You are all welcome to go take a look. Find any bugs, please report them. We host this package in the GitHub organization that's called Open Source Ocean Acoustics. This is a GitHub organization we created with a hope of having a place to either hosting code or just as a hub to point to existing resources or developing resources in this domain, because the online presence for ocean acoustics is not super high right now. And with that, I also wanted to acknowledge other contributors for Echopype package on the left. And on the right-hand side are developers for PyEchoLab. And I just wanted to mention that briefly. PyEchoLab is an effort that was supported by NOAA, and they basically unpacked one type of specific Sonar data but they base everything on NumPy, which has a different philosophy. But we did use some of their low-level data processing routines. I wanted to acknowledge their contribution. And I hope you would consider joining us to help us tackle this problem. And I'll end the talk with the vision that we discussed earlier. I'm happy to take questions.
Really nice talk. Okay.
Thank you. That was great. Are you in contact with anyone from the inland water community, surface water? Because right now there's an effort in the USGS to do calibration of backscatter from ADCPs for sediment transport. And
that's cool.
That's a huge application that this might be useful for, and in the coastal community as well.
That would be cool.
Hi, thanks. Are you able to interface directly with the Sonar devices from Python? And if not, how does the data get sent to the database?
So right now, we haven't touched that part at all. We are just dealing with archive data currently, yeah.
Hi, I'm mostly a modeler, but have started to deal with observational data and want to do that more. And recently I was dealing with some Acrobat data, which was saved in an NC format, but with horrible metadata. And when I asked the people that are in charge of that, what they have told me is that every company have their own secret conversion filtering thing that you have to get, and you don't really know what's happening in there. And I was kind of looking at your code, and I saw that you have a convert EK60 and convert AZFP something. So I'm guessing those are companies. So how do you deal with that? How do you get out that secret code?
Secret code. So a lot of companies are, their secret are actually open. Right, so they're open about how their data is formatted. And I guess it was probably a choice, but like for example, the AZFP echo sounder was produced by this company called ASL Environmental Sciences. And when I contacted them, they were like, yeah, great, you want to do this? Here are the MATLAB code that we use, that we give people to parse the data. If you have the Python version, please send us the link so that they can connect their customers to do that. Right? So I feel like there could be a healthy relationship between the companies and the kind of wider developer circle or just a user circle, even with the proprietary software companies as well. Does that make sense? Did I answer your question?
Any more questions? No? Okay. Well, thanks so much again, Wuzheng.
Thank you.
And just a reminder, we have one more talk tomorrow. So if you're around, come check that talk out.